usual in English. This time, today's speaker is Danil Polykovskiy. His presentation was postponed twice. Sorry for that. But finally, the last talk in this semester, you'll have a chance of presenting us talk about differentiable data structures, or how to do next step on the LSTM networks, and how to transform them to what is sometimes called a neural computer.
Right. As the title suggests, I will talk about the major steps that have been made since the invention of well-known LSTM networks to the so-called differentiable neural computer. So, what is neural computer? It is a kind of neural data structure that is fully differentiable, so you can train it with backpropagation, and it resembles the usual personal computer. So,
speak a bit louder.
Okay. So it resembles the usual personal computer in the following way. It has the controller, which resembles the central processing unit, and it also has the memory, which is controlled via allocation mechanisms and also the free operations and so on. So it really looks like a usual computer. So why are we interested in such things? There are two worlds, the algorithm worlds and the neural network world, which have the gap between them. So there are some problems that can be solved with neural networks, and some problems which can be solved by algorithms, but not replaced. So, and our goal today is to narrow the gap between these two worlds. So let's consider the example of some problems. So, first of all, let's see a cat-dog discrimination problem. So, if we would try to write a program in, for example, C++ that will discriminate between dogs and cats, well, we would probably write some kind of discriminator that will find the heirs. If the heirs are lop-paired, then it is a dog, and if those are point heirs, then probably it is a cat. But there are some special kinds of cats that are lop-paired cats that will be misclassified. So this is a problem with handcrafted features. Alright, so another problem that can be solved by algorithms but cannot be solved by neural networks is sorting. But there are two kinds of sorting. One sorting is sorting into the finite number of classes. So actually this is just a classification problem. If, for example, have a head that should discriminate students between faculties, then, for example, when the new student comes, he can, the head may predict that, for example, this student is from Hufflepuff.
But this is perfect classifier.
Yeah. So the harder case is when the number of possible classes is infinite. So, for example, sorting of sequences. And this, as experiments show, is a really hard problem for LSTM networks. Alright. So, as an appetizer, let me show you this plot. The blue line is the training curve of LSTM, and the green and the red lines are the training curves of Neural Turing Machines. And this is a task of sorting sequences. So you can see that the Neural Turing Machines perform much better than the standard LSTM architectures. Alright. So the plan for today is we start with attention mechanisms, then we proceed to Neural Turing Machines, briefly talk about them, then we talk about neural stacks, DEX, queues, double linked lists, and so on, so popular data structures. And then we will finish with differentiable neural computer, which is the slight modification of the Neural Turing Machine. Okay, so attention. The mechanism of attention is based on the notion of saliency. So saliency is the salient regions are regions of an image that quickly pop up when you look at them. For example, if you look at this image, you will quickly notice the red dot, which is salient because of its color. Another example is saliency because of orientation. So here you can see the line that is vertical, and it quickly pops up because all others are diagonal. The third one is saliency by size. However, those are just simple examples of saliency. There are much more interesting examples when you see normal images. For example, when you see this image, you quickly focus on the eyes. So eyes are usually salient. Okay, so how attention works. We usually have some finite number of features. For example, for words, those would be embeddings of the words. For example, we have the sentence, the red boat sank, and you would have some embeddings of these words, vectors. So some auxiliary network, which we'll call attention network, will generate the distribution over those vectors. So for example, if we consider the task, what color is the boat, and the answer would probably be yes, we could say that here's the word color. The color is similar to red, so the weightings should be like this. Red is 0.9 and some residual weights for all other words. And then we compute the weighted sum. So we take the word D with that small coefficient, we add the word red with coefficient 0.9 and so on. And so finally this is the formula. So this is the case for the texts. Another part is images. So it is actually not really interesting to compute the expectation over pixels because it will give you some kind of average color. So what you do is you pass this image through a network until some layer, for example the 13th layer, I don't know, and take the feature maps from that layer. And then you apply the same attention mechanism to those feature maps. And you can visualize where the attention, where the network looks by, for example, taking the most attended regions and highlighting the receptive fields of those neurons. So for example, for this image, you can see that neural network concentrated on the bear. So here is actually a child holding a bear, and network quickly finds the bear. Okay, so actually those were images from this paper which focused on caption generating. So the architecture was as follows. They had, as I said, the network. They took feature maps from some deep layer, and then ran an LSTM that tended to some different positions of an image. So, and at each timestamp it generated a word. For example, here it generated a bird flying over a body of water. So yes, here is a mistake, a body, but you can see that when it generates the word bird, it attends at the bird. So you see here the white region, it is the bird, and for the water, it attends everywhere but the bird. Okay, so neural Turing machines. So what is a Turing machine? Well, it is some kind of mathematical abstraction of a computer, which works as follows. It has an infinite tape, which has some symbols written in each position. And also it has a controller, which attends to the specific element. And at each iteration, it can either move the head to the left or to the right. So it has some internal state, based on which it guides its decision. So each iteration takes the current value, takes the current state, and produces the new symbol for this element and an action, which can be either move the head to the left, move the head to the right, or stay here. So there is a cool notion called the Turing complete systems. We will be really interested in them a bit later. So Turing complete systems are systems which can simulate any possible Turing machine. So for example, a lot of modern programming languages are Turing complete. So here are some questions for you. Are recurrent neural networks Turing complete?
Yes.
Yes. Okay, why?
You can implement anything with them. I mean,
yes, actually, yes. You can simulate, for example, internal state by the outputs, or, for example, if you have an LSTM, the tape would be inner memory and the state would be the current output. Okay, so the answer is yes. The less trickier question is is it possible to train the neural Turing machine with backpropagation? So the answer is no, because the operations are discrete. For example, you cannot differentiate the action move left or move right. So the guys who like reinforcement learning may say that well, you can train it with reinforcement learning, but it turns out that it would need a lot of iterations, and we also want to have a fully differentiable data structure, so we would be able to connect a lot of them together also, and so on.
I didn't get the last point. What do you mean by wanting to connect them together?
Well, for example, we will now consider neural Turing machines, then we'll consider neural stacks.
Okay.
For example, you would like a neural Turing machine which would be connected to a neural stack and so on, so a more complex abstraction of memory. And if we connect those together, it is harder and harder for training by reinforcement learning.
But it's harder to train by backpropagation
As well.
Whether
Well,
So in theory, this is possible.
yes,
In practice,
okay.
not.
Yes, sure.
And by reinforcement learning, you probably mean reinforce algorithm, capital letters.
Yes.
Reinforce.
Okay, so here's the high-level architecture of neural Turing machine. We have the controller here, which will be some kind of neural network. It has read and write heads which control the memory. So the memory is just a matrix. It has dimensions n by d. N is the number of cells in which we can write and from which we can read. And d is the dimension of each cell. There are two scenarios in which we can...
Sorry, and the size of memory is fixed.
yes.
Because in conventional Turing machine, it's not fixed. The tape is
yes.
considered to be infinite.
In conventional Turing machines, the tape is fixed, but it doesn't need to be infinite if you have some bounded input size. So, for example, if you're bounded with numbers less or equal than, for example, 2 to the power of 31, you will fix some number of elements that you'll need and use only them. Okay. So there are two scenarios, the read-only and the read-write. So actually I want to argue that read-only scenario is a really important thing because it can learn some useful features, some useful concepts that it would be able to store in this memory. So for example, if you are talking about colors, you would have, for example, some vector that is responsible for finding all the words that are about color. Okay. So now let's talk about the read heads. The reading is done as follows. First of all, the controller generates the vectors, the weightings vi for each memory cell. And then it is transformed to a distribution with temperature beta. So the beta will control how sharp our attention is. For example, if beta is large, we will attend only, for example, one cell, and if the beta is small, we will have some blurry distribution. So, and then we compute the weighted sum with weightings generated by this form. Okay, so now the question is how we generate the vector, the weightings vi. So the usual form is so-called focusing by content. So we take some key, like in associative arrays or dictionaries, using which we want to retrieve. For example, the key could be the word red, and then we would like to attend all the cells that are about the color red. So we do this by applying some function k, which has two arguments: the k, which is the key, and the position. And for k,
sorry, but this position m of I, isn't it the same as the content of corresponding memory cell, or are they different things?
mi is the content of the corresponding memory cell.
Is it really necessary? It seems that mi should be the key for the memory cell. But the content of memory cell could be different.
Yeah, sure, but that's what they did. So actually, that's a good idea to have a separate key and the memory, but having those together is still useful because, for example, the key can be, for example, some key and then it can be filled with zeros. So this would be the case that you told us about. Okay, so let me draw this. So this is our memory. For example, we would like to use this part as the key and this one is the value.
Right.
And the vector key would be something like this. It would be some A1, A2, so on, AK, where K is this size.
And
others would be zero. And when we compute the scalar product, and here the kernel is usually used as a cosine similarity measure, then those values would be ignored. Okay, so this is just more general case.
But the problem is that as a weighted combination, we'll take both value and key in the previous slide.
Yes. But then, again, the later levels of the network would probably learn to ignore the key. This is possible.
Yes.
Okay. So with this mechanism, we can model associative arrays. So another example is focusing by index. So with focusing by content, we are not able to do some things like iteration. For example, you usually write cycles like loops like for I in range, so on, and it is not possible with content. So to fix this problem, they proposed a really cool algorithm, but let's for beginning consider the bad version of it. So the bad version is, as here, you could add a separate key storage, and then the kernel would be a difference between the first elements. So this would allow us to index values. Okay. So it is possible for a network to learn this. However, it turns out that it is a really bad decision. A bit easier decision is to use this thing. So you take the previous attention vector. For example, if you attended to the word boat in the previous case, the red boat sank, and you would like to attend to the previous position. You output a kernel for the convolution which has a size 3, and you convolve the previous attention vector with this kernel. And actually, you also do this with a circular convolution. So if you go out of the boundaries of the array, you jump to the beginning. So here, for example, when S is 0, 0, 1, after the convolution, all the weight vectors would move one step to the right. Okay, and if we had, for example, 1, 0, 1, we would be able to do something like I minus minus. Okay, so now let's write the whole formula for the reading operation. Okay. So let me erase this. Okay. So here how it goes. We have the previous memory state and the previous attention vector. And we generate a whole bunch of auxiliary variables. So first of all, we perform content addressing. So the WTC, C stands for content, and the position I is just a softmax of the cosine similarities. So it is e to the power of beta times kernel of the key and the memory state in the position I. And then we normalize it by dividing up to the sum of over g of p times power beta kernel k mt in the position j. Okay. So we've seen it already. So then we perform interpolation, which will allow us to switch between this mechanism and indexing mechanism. So WTG actually is just a gate at the timestamp t times the and this one. Yes, at the previous timestamp. Let's write it like this. All right, and plus 1 minus GT times the context vector, like this. All right, now we perform the indexing. For this we do following WT till I, right, let's write it like this, equals WTG convolved with S. So here's one problem.
One question. The form of S, is it somehow fixed? Is it obliged to be binary or can be arbitrary convolution?
No, it is arbitrary convolution, but it has to sum up to 1. Usually they use the convolution of size 3, so that you will be able to move one step back or one step forward.
Yes, but the movement back and forward will correspond to the case when our convolution kernel is binary.
Yes.
But if convolution kernel is not binary, then there will be some scattering.
Yes, sure. So the problem here would be that we will blur our focus. So for example, if S is like 0.1, 0.1, 0.8, then you're pretty sure that you wanted to move right. However, due to these values, your focus will blur after a lot of iterations. So for example, if you attended only, for example, ith element, at the next timestamp it will be more blurred, at the ith plus 1, and so on. And so on. So to fix this, they decided just to sharpen this distribution. This is done by emitting the value gamma. So WT, the final read vector at the position I, is just the WT tilde at position I sharpened. So we just put it into the power of gamma and renormalize it. Sum over J, WT at the position J tilde in the power of gamma. So here are the formulas. Okay.
But why do you need interpolation? Why do you need interpolation?
Yeah, that's a good question. That's what I'm going to say now. So if we have the gate equal to 0, then this part would be ignored, and all we have here is the indexing by indexing, right? And if we have G equal to 0, then we will ignore this part, and we will have only focusing by context. Okay. So we're mixing the two different types of attending by this gate.
Wouldn't it make sense to mix, so you have WC, which is like content based,
Yes.
and you have WT, which is, W tilde, which is after the convolution. Wouldn't it make sense to interpolate between them, between W tilde and W constant?
Yes, actually there is a mixed scenario, which is focusing by content and then instant iteration, which is really useful, for example, this case. So again, the red ball sank. What color is the ball? Yes. So in the beginning we thought that it may focus on the color, but here let's consider that it focuses on the boat. Because for example, if the sentence was the red boat sank and, for example, something more poetic, the color was blue, then it would probably take the red color, the blue color, mix it up and get a purple color. So alright, so it decided to attend the word boat. The most similar word to the word boat is boat. And it iterates one step back to get the color. Because it is really intuitive that the color would be right before the noun. Because, well, you wouldn't say the boat red sank. Okay. So if we did it in the two separate iterations, we would probably have to remember the word boat. Then we have to somehow remember that we wanted to index it back. Actually,
Okay.
I think it is possible to switch this interpolation to here, but it won't be possible to do this thing in the one run.
Okay.
Okay, so now the right hat. The writing is really easy. We do this in two
Can I ask
Yeah.
now a question? So, the red boat thing, was it the memory or what?
First of all, we input this vector as a context, like an input. Then we give it some signal that we are now producing giving it the question. Then we produce the question. Then we give it a question, and then wait for an answer.
I mean, what is memory here? What is M?
Memory is some memory bank which is somehow trained. So while you will be going through this sentence, you hope that the network will store all those words sequentially in the memory.
But you don't have write.
Yeah, that's what I'm going to talk about.
So
Right.
this doesn't work. Then you don't have write operation. Right?
For this case, yes.
Okay.
Right, so now let's talk about write head. So it is done with in two steps. The first one is erasure step, and the second one is adding. So this is how you do it. You output the erasure vector, which, for example, if it has all ones, then it would erase everything from the attendant cells. And you also have the waiting for each element.
Is it the same as the waiting for previous
No.
one?
So the read heads generate its own weightings, and the write heads also generate its own elements, but with the same mechanism. Okay. So then you, after you erased, you add a new vector, the new value that you want to store. So for example, if you had this value equal to 1, then you would first of all erase this element and then add a new one. So here's a little problem. If you have multiple write heads, then running this formula asynchronously will lead you to some arbitrary result. So it is not serializable, which means we would like it to be commutative. So we'd like to update commutatively.
Sequentially. One by one.
I mean, we don't want to care about the order.
Or we may fix the order, alternatively.
Yeah, okay. But we are really interested in parallelizing this thing, because this thing really works really slowly.
Mm-hmm.
Okay, so what is done? You first of all compute the first part, and since here is only multiplication, this is commutative. And then you compute the second part. So you wait until all the write heads finish here, then you compute the second part, and again the addition is also commutative. So finally you have the asynchronous update here. Okay. Now let's talk about controller. There are actually two main approaches to implement a controller: the feed-forward controller and the recurrent controller. If we consider a recurrent controller, then we have a good resemble with the personal computers. So the controller is central processing unit. The memory inside LSTM is some kind of registers, which can be used for some intermediate computations. And the memory bank is random access memory. So this is the recurrent controller. Another one is the feed-forward controller. So first of all, I have to notice that we can use a really deep controller, which will probably be able to simulate the LSTM, because we will run it for some fixed number of iterations. But this controller is better in the case of interpreting the results, because we will be able to see the positions into which the controller attends. Okay. So let's now look into experiments, and then we'll come back to our talk. Okay. So,
Wait. I still didn't understand what is feed-forward controller, how it works.
it takes an input. Let's here. So it has input.
Mm-hmm.
It is some feed-forward network, so convolutional one or a fully connected one. It then outputs the vectors for the read and for write.
You mean these W's?
Yeah, W's. So they generate a separate one for the read and separate one for the write.
So controller defines the weights.
Yes.
The weights that are responsible for the memory elements which we would like to read from or write to.
Yes, actually, let's see to these formulas. Let's circle out the elements that are generated by the controller.
Mm-hmm.
So first of all, it is the key. It
Right.
is this temperature. It is this gate,
Mm-hmm.
right? It is this kernel, and this sharpening coefficient. So 1, 2, 3, 4, 5.
But this is for each head.
And for the right head, same.
Right at the same.
And it is also possible to have multiple read and write heads.
Okay, but then what is the difference between feed-forward controller and this recurrent controller?
In architecture,
I think the recurrent controller does have a short-term memory, so it has some like, these registers or something.
Registers, they're responsible for the
intermediate computations.
for the work of controller. And in feed-forward, there's no short-term memory for the controller.
Yes.
But in principle, you can put anything you want in the memory, but it can be hard just to learn to do.
Mm-hmm. Okay, so I agree that these are two different types of architectures, and probably they should result in different memory networks with different properties.
Yes. Alright, so let's consider some examples. So first of all, it is the copy task. In the copy task, you are provided some sequence, and you are asked to output the same thing that you got in the input. So the networks were trained on the elements of length 20, and the authors were interested in whether the network can accommodate to larger sequences. So for example, here we have the LSTM network prediction on the length 20, on which it was trained, and it does the output perfectly. However, if we twice the length, then the errors start to occur. So you see errors here, you see errors here, and on the longest sequence of length 120, you see the whole bunch of errors. However, Neural Turing Machines perfectly learns the task. So even on the larger sequences, it produces correct outputs with a small number of mistakes.
Did they increase number of memory cells?
Actually, as I remember, no. They trained on some fixed number of memory cells. Actually, the cool thing about Neural Turing Machines is that it can be run on arbitrary number of cells. So for example, if you train it on the memory size of 20, then you can, without problems, run it on the memory size of 40. Because this formula can be computed, yeah? Because this attention, this one also, this is just a convolution, and again, this is just a convolution.
But you have to relearn the memory bank, right?
No, the memory bank is initialized with zeros, for example, and then...
Yes, but you have to increase the number of items in this summation.
Yes, but no extra weights need to be trained.
So does it mean that we may simply set the size of memory before the validation phase? So we have Neural Turing machine, and we may say, okay, let us now validate it on some data with a memory size equal to 20. And then let us validate it on different type of data with memory size equal to 100.
Oh yeah, it is possible.
It's possible, but I don't think it's a very good idea.
I don't know.
Well,
This is what Danil says.
I say that this is a cool property, but I don't say that is what you should do.
Yeah.
Okay. And what does this header on
Yes. Okay, so here's the sequence of length 120. It does some small mistakes, However, in this place, it outputs the same element twice, and so all these vectors are shifted by 1. So the validation error would be huge, because all those pixels are wrong, because they are shifted by 1.
And the shift happens here, where the
Where
right
the-
arrow
the red
points.
arrow.
I didn't get it. Why the shift happened?
It was just a
Nobody
mistake.
knows.
So it's like you're saying that neural Turing machine has different types of errors, but it, like in principle, it's doing something reasonable.
Yes.
In this case.
Yes,
So
yes.
the edit distance is fine, but heading distance is bad.
And
Yes.
then you talked about read-only memory. In that scenario, you assume that you like pre-train the M.
Yeah, you pre-train
Okay.
that. And for pre-trained memory, you cannot increase the size.
Mm-hmm.
Sure.
All right. So let's now try to understand how it is able to solve this task. So here are the inputs, here are the outputs, here are the weightings of additions and reads. And you may see that it starts in some position and then writes all the data into sequential positions. So indexing mechanism is really useful here. And during the output phase, it attends to the first element and then reads all the outputs sequentially again.
Can you please repeat what is these black rectangles?
Yeah. So here is time, here is location. Each column here is the timestamp. Each row is the element of the memory,
Element of what memory?
of our memory, of the matrix M.
Okay, and
So
what does white square mean?
Yeah, and the white square means the attention. So this one means that we attend to this location. And this
So
one,
we are reading from this location.
yeah, we're reading from this location, and here we're writing to this location. Here we're reading from this location.
And here the D equals 1, right? Like the
No, actually, this is just the indexes.
Oh, okay.
So this is like, I think this is this vector. Or no, sorry, this vector. Not the values, but the attention vector. All right. So again, it is really interpretable. You write sequentially, you read sequentially. So, and for the learning curves, you may see that LSTM isn't able to solve this task perfectly, but all the Neural Turing Machines solve it perfectly with a small number of iterations.
But this is quite a specific problem. This is very suitable for neural Turing machine.
Yes, and so are all the other
And
experiments.
can you design by hand the weights for LSTM to solve this task? So can you say like that the backpropagation failed, but in principle you can find the weights that will solve it reasonably well?
Well, the LSTM is Turing complete, so probably yes.
I mean, you have
Not
to
for
make
long
it.
sequence.
Yeah, you have to make it like extremely large.
Yes. So actually, here the main point is that it is able to learn for some fixed length, but it isn't able to interpolate to longer sequences.
If you increase the size of memory for the larger sequences,
So I remember they kept the fixed numbers.
And why first step it reads memory and after that it writes?
Yes.
And why it can do mixed steps? Read and write.
It can-
Read data and output results.
Well, it can do the same. Wait, you mean why doesn't it like cheat and output?
Yes.
Well, because the outputs are read only after the input stopped producing.
So we first read all the input,
Yes,
and then we
you-
start producing
yes,
output.
Yes.
So we have somehow to keep all the input in memory
Yes.
in order to solve the problem.
But furthermore, we want them to be sequentially stored or somehow to be able to restore the order.
Yes.
Just can you tell just the exact amount, value of the memory for the both cases?
There were, as I remember, there were 20 floats.
So 20
You
cells.
mean the memory M or the memory inside the
The D.
LSTM?
The memory M.
And what about inside the LSTM?
Uh,
Cells?
They had like 400 neurons each there.
But you said that like M is a matrix, right? What is
Yeah.
the dimensions of this matrix?
The D is 20, the N I don't remember.
But it's larger than the length of this bottom sequence.
Yes, this is a very interesting question.
Yes, it is. Otherwise, we would have.
Paradox.
Yes. Okay. So you would actually have interference if you would override the same positions. Okay. So a bit harder task is repeat copy. So you are first provided a number of times you have to repeat the input, and then you are given the input. So for example, this is the input, and the first bit is the number of iterations. So how it does it? It stores into this position the number of iterations, and then it stores the input. And during the producing of output, it attends to the number of elements, the number of repeat reads that are needed to be done for completion. It subtracts 1, for example, from here, then it provides output.
But if it subtracts 1, shouldn't be the attention in the right weighting, in corresponding position, where the index is kept?
I think I think it remembers in the LSTM part. Okay, sure. Okay, so the cool thing is that it is able to automatically terminate. So if, for example, here we asked it to provide 5 copies, then it automatically generates some stop sign. For example, like end of line. Okay. So another task is associative recall, which is you're given a sequence, and then you're asked what was the element that was after the queried one. So, for example, here's an input, this one, and this is a query, this green box, and you would like to output the one that was after the green box, so the red one. Okay. So again, it stores all the stuff in the memory, and then it quickly jumps to the init position, and then outputs the queried element. So the cool thing here is it somehow learns to encode the whole picture. So you start reading those elements, then when there is a gap between the previous element and the next one, you write the embedding of this picture to the memory.
How do you know that there is a gap?
The dot here. So we give it some time to remember stuff.
And can you repeat the previous example? In this example, is it right that this Turing machine learn how to perform simple operations such as subtract or add? Because it doesn't any code. How it learn how to subtract data from the counter?
Well, I think it is an easy task for the LSTM to somehow decrease the counter inside itself.
This is true. LSTMs can do that.
And is it work for any size of number of copies?
Well, actually, they said that if they train it on, for example, number of copies from 1 to 5, it generalizes to a bit longer sequences, but fails to a very different number of copies.
Okay.
Okay, so associative recall, the coolest one is sorting. So we are given some data, and for each column we have some sort of priority. And then we're asked to output top k elements. So for example, this one is high, so this one should go first, and so on. And it really does solve this problem. So it sorts the elements and output the highest ones. Okay. So if you consider the weightings, the right weightings look like this. So it performs sorting. And actually, if you fit linear model to the positions, then you would be able to predict. Those are predictions, and those are actual weights. that it tries to estimate the position of the elements by having the new priority. So for example, the last part was here, you wrote here, then you see that the new number is quite large, so you try to move as far down as possible. Because this is the largest one for now. Okay. And for the as for the reading, you just read it sequentially. So you sorted the sequence. Okay. And so the image from the advertiser, again, the LSTM networks fails. Well, it does something useful. The bit error rate is 120 is complete nonsense. It's like generating a random output, and this one is pretty great. So the cost of 20 is a good result.
But we can always sort 10 numbers or 100 or 1,000 numbers.
No, small
It
one.
doesn't work for very long sequences.
But still, they work better.
Then LSTM, that
Yes.
almost do not work. Brilliant result.
Well, actually, the point of this paper is that you can build another architecture, not just the vanilla LSTM, but with memory that will outperform on some algorithmic tasks.
This is what is called proof of concept.
Yes.
But conceptually it works.
Does this sorting depend on the distribution on the sorting array?
Yes.
Yes, the inputs were actually generated from uniformly from -1 to 1.
And I think it also depends on the length of the
Yes,
sequence.
on length, sure. It can not generalize to the much longer sequences. Okay, so now here's one paper I accidentally found. This is called the Structured Memory Neural Turing Machines. So the authors proposed 3 architectures which modify the memory bank. So first of all, what you could do is to have the hidden memory. So now you have the MC, that is a controlled memory, and the MH, which is the hidden memory. And now you can, as you can see, you are not able to write to the hidden memory, but only to the controlled one. And the values of the hidden memory are computed as exponential average of the values of MC. So it does not allow the rapid change of the values of the memory. Right? And so the reading performs only from the hidden. You can move a bit further. You can divide it to. You can divide the write heads to the first and to the second memory bank, which would recall the L1 and L2 caches from the computers. So, and a bit more further, you can
And further and further and
you can create 2 different controllers, one for the L1 memory and a different one for L2 memory. Okay. So I think it is really cool because, well, computers do have different caches. So now here we have registers, here we have L1 cache, here we have L2 cache.
But what's the point? Like in computers, the point of making different caches because like fast memory is expensive, right? But here, what's the point to make them separate?
Well, actually, they argue that this is for protection. So you don't allow the rapid change of this.
yes, but
But
with
in the second-
V2,
Yeah.
with W2.
I think
We
they
do allow.
Yeah, they do allow, but they still average here. You see, here is no weighting, so you just compute the average over those positions and modify it slightly with this vector.
Who told that it is slight modification?
The formulas. So if you remember the update formula, you are not able to erase the whole memory. Okay. All right. So now let's jump to the second part of the talk. Those are neural data structures.
Well, can you
Okay.
return to the truth? How authors choose between these 3 types of architectures? Which are good, which are bad? How to
All
feedback
right.
the
So
model?
actually, they have quite questionable results. They have 0 citations, and it is. And I really found this by accident. I think that it is a really cool concept, but they have really strange results. So they provided a number of experiments in which they showed that sometimes neural Turing machine works, sometimes neural Turing architecture, this one works, and so on.
But do they have any explanation why
No.
this works, this one doesn't
Just
work?
like our students and their
How
reports.
they debug the model? What picture they constructed?
Well, they provided, it is actually a paper that is 2 pages long, and they have these pictures
And one of the pages is with
Yeah.
pictures.
and the comments on this. And in the end, I have a couple of training curves.
Does it make sense to use this kind of NTM things in tasks that are usually solved by LSTMs, like, I don't know, machine translations or something? So, like, at least in principle, I mean, maybe not now, but like, what should happen to make it practical for usual tasks?
Well, I think this architecture is really near the one that should be used. But, all right, for machine translation, you don't need a lot of auxiliary memory. You probably need to store the previous values, but for taking previous values, there are attention mechanisms for texts. So you don't need to store them in a separate memory bank.
But if you need a lot of memory, then you need continuous.
Alright, so why are we even interested in neural data structures? So we've covered neural Turing machines are great. Why neural stacks? So one point is that if we would like to increase the, if we would like to dynamically increase the number of memory, the amount of memory we have, then we'll probably need some dynamic data structures like double linked lists, like stacks, queues, and double-ended queues. So another example is that learning Turing machines is really hard. So
just one comment. I think neural Turing machines are used in translation already, and there was a recent paper by Google where they showed that this model is kind of state of the art now.
Okay.
So they have like 30 authors, including Jeff, in this paper, so I would believe them.
okay, so programming programming Turing machines by hand is really hard. If you remember from discrete mathematics, it was not awful, but not the pleasant one. So, and the last point is that when you have neural stacks, when you have stacks, you can solve some problems like reversing the data and so on. So, when you write a program, you usually use those structures and not the Turing machines. So, again, the stack is discrete, so we'd like to somehow make it differentiable. And the idea is that we include a notion of strength in which the vector is present in the stack. For example, here we have vector v1, which is present with the strength 0.3. The vector v2 is present with weighting 0, which means it is absent. And the maximum is 1. And so here's the vector v3, which is present with value 0.9. Alright, so now let's describe the 3 main operations for stack, the push, pop, and head. Alright, so push. We want to push some vector v with strength s. To do this, we just push vector v2 into the normal stack and assign the strength to it, the one that was asked. Okay. So the pop, you do as follows. You run from the head to the bottom until you reach the total number of s. So for example, here s is 1, you start with this value, here is 0.5, you put it to 0. Here is 0.8, and the residual from this one is 0.5. Okay, so we used 0.5 here and 0.5 left here. We subtract 0.5 from here and get 0.3. Okay, so, and the head operation is made in the similar way. So you just go from the head to the bottom until you reach the total sum of 1. And then you compute the weighted average. So for example, 0.5 from here, and all we have left is 0.5. You take it from this one, and so this is the formula.
So what happens if you fail at either of these iterations? Like when you try to push something to the stack, but you already exceeded the allocated space you have, or if you don't have any elements that would be at least S.
If you don't have the memory, the total sum at least S, well, you have, for example, underneath this some vector of zeros with the strength infinite. Okay. About the memory, if the memory on your computer ends, that's your problem. And
Stack Overflow.
yeah, it's like Stack Overflow. But here you can have possibly infinite number of elements. So you dynamically grow the structure.
Okay. Okay.
All right. So neural stack.
This is not the previous slide. What is head?
Head is for the conventional stack is the top element.
Ah,
Just pop with S equals 1, right?
No, it's not pop. You don't modify the weightings.
Oh yeah, right.
Just read the topmost element.
mm-hmm.
But it works like the pop operation, yes. Okay. So all right, neural stack. The controller provides us at each iteration with the push strength, with the pop strength, and the value that we want to push.
Mm-hmm.
And the output of the neural stack is the head vector. So the simple question is, what do you do first? Do you pop first and then push, or do you push first and then pop?
No, probably you first pop and then push.
Yes, sure. Because
Otherwise, we'll pop
you-
the element which
yes.
we have just pushed.
Yes. Okay. So queues and double-ended queues are constructed similarly. So you, for example, for queues, you would push to the last element and pop from the first element.
And what is DQ?
Double-ended queues. So those are structures to which you can push and pop from each end. Okay. So actually the authors argued that if you just try to train this network, it would fail because it will not explore the possibilities of the provided data structures. And so they try to somehow force it to explore the memory. So, and they did it simply by adding some bias for pushing. So now you constantly push something in the first few iterations, and then probably the network will learn the optimal way to solve the problem. Okay, so double linked lists. So this is a data structures in which you can you have a head, and you can move the head either to the left or to the right, and you can read the current value, and you can also insert a new value. So here are the operations, and
Can you delete the value?
well, actually, I think they did not delete in the paper, but it is easily added. So we have three operations for each of which we can write a formula. So for example, move the head left. So to the ith element, we would need to write the I plus 1th element, right? I minus 1th element. And to move the head right, you would need to assign to the ith element I plus 1th element. So you move head from here to here. So the ith value is now the I plus 1th value. Okay, and to insert a new element, you would have to move all elements that are to the left of the head one step to the left, all the elements that are to the right or the head to the right, and then insert a new value. So this would be this formula. So if we're to the left, we move everything to the left. If to the right, then we move it to the right. And to the current position, we insert the vector E. Right. Again, we have a problem. We have to somehow choose between the three discrete operations. How do we do? How do we modify these discrete formulas to make them differentiable? And the answer is the weighted combination. So again, the controller outputs three scalars, A, B, and C, each of which is responsible for different kind of operation. So this is again differentiable. Okay, so the last thing I want to talk about is the differentiable neural computer. So this is a slight modification of the neural Turing machines that we've talked in the beginning, but it has a different mechanism for managing memory. So for example, it will have a separate memory allocation filter that will not allow us to write to the already used positions. Okay, so let's now start with some philosophical question. So the many philosophers argued about what memory is, why do we store memories, how do we store them in our mind. And John Locke argued that the memories in our mind are connected if they occurred in the nearby time and space positions.
And or?
I think he said and, yes.
And he meant or?
Well, yeah, I think from my experience, the positions that are nearby in time are also nearby in space. Because
but some events that are nearby in space can be can happen in different
it's okay.
in different time.
Here, I think I'm not him, so I think he mostly meant the time, and we will now be interested in the time position. Okay, so here's an example. So, for example, what you see here, you see a New Year tree. It has some cool lightings. And what was the first thing you thought about? So probably it was New Year, some presents and so on. And why? Because we had experience in which the presents were gifted after we saw the Christmas tree. When we were kids. Okay, so the conclusion from that picture is that we can arrange the memory as a graph. Because we now have the events that are near in time, and we can provide edges from the previous events to the consecutive events. Okay, and so we'll have some sort of a graph. Okay.
You mean a chain or like any
Well,
graph?
yeah. Actually, in the perfect situation, it would be a chain. However, we sometimes remember a few events that are somehow similar. So, for example, you saw a tree, you saw lightings, and then you saw a present. Okay. Well, like we had event 1. Event 2, and those two went to event 3. Okay?
I would suggest not to discuss how human memory is organized because nobody knows.
Yeah. Okay. So, all right, but let's discuss the organization of the differentiable neural computer. So the memory is organized with the so-called adjacency matrix for it, and let me write the formulas for it. Okay. So the adjacency matrix is of the size n by n, where n is the number of memory cells we have in a memory band. It is a directed graph, so you don't expect it to be symmetrical. And also you would expect the diagonal weightings to be 0. So Lij is the strength of how it would be equal to 1 if event I occurred after event j. And it will tend to 0 otherwise. So again, if it was changed, it would be...
Simply after, or they're related with some causal dependencies?
Not simply after, but it depends on how much you write to the memory. If you didn't write, for example, for 5 timestamps, that then the previous one would be still the one that you wrote. The 5 timestamps earlier.
Okay.
Okay. So here how it goes. So first of all, you output the so-called precedence vector. Precedence vector, which says which elements we have written to in the prior timestamps. So it is pt, which equals to 1 minus sum over I w t right. This is the output of the right head at the position I times pt minus 1 plus wtw. Alright, so let's discuss this formula. First of all, they modified the notation a bit. So in the previous timestamp, this thing was forced to sum up to 1. But now we consider the vectors such that some of its elements are less or equal to 1. So they have a new memory position which is capable of something called like no operation. So for example, if all of those weights are 0, then you simply do nothing. Alright, so if we write with the full strength, so the sum of w's is 1, then this term becomes 0, and the precedence vector is just the distribution of the positions that we've wrote. So for example, if this was like that distribution, then the precedence vector would be all zeros but 1 position. Okay. So after the precedence vector, we compute the linkage matrix. So linkage matrix. So L, for the diagonal elements, we force them to be 0. And for all other, we force it to be this one. So it is 1 minus WTW at the position I minus WTW at the position J times the previous value of the linkage matrix. So this is at the timestamp T, and this is at the previous, so IJ, plus the new value, which would be WT right at the position I times the precedence vector at the previous timestamp, the position J. Alright, so let's try to interpret this formula. So, first of all, we update the values of the linkage matrix if we make the values, the edge between I and J nodes stronger if, first of all, the J was precedence, so it was before, yes, and if we wrote it to this position, to this it's pt minus 1 because it is in the previous position. We're interested in the previous vectors. So for example, if in the previous timestamp we wrote to the element 2, we want this one to be 1 in the position 2. Okay.
No, this part seems to be reasonable.
Okay. And also you update it with this coefficient. So, for example, if some of those was 1, you would not update. And otherwise you forget a bit. So if you wrote to the position J, then you should lower the strength of the connection of I to J, and the same for the I. Okay. Okay. And
Yes.
finally we output the read vector. So the read vector, which is computed as follows. We have 3 options. We can move through this linkage matrix to the future. We simply, for example, if W is the weighting, and we multiply it from the left by the linkage matrix, then we will follow the graph along the edges. if we multiply it by the transposed matrix, then we will go one step to the past. And finally, what we do, we compute the average between going to the past, going to the future.
And what is the purpose of doing that?
Well, to make it differentiable. So, so you, for example, compute like this, P1, P2, actually take the read vector from the previous timestamp.
And P is in attention or something?
No, P is, well, yeah, it is some distribution which sums to 1.
Yeah,
That's one error. And also you add the pi3, which is the result of the content-based retrieval. So this is, they denoted it by CT. Okay, so this is what was called in the previous paper WC, so the context retrieval. Okay, so this is the one part, and the second one.
Why do you want to go to the future? Why can you omit the? So what's the purpose of going to the future?
Well, actually, you see that here is t minus 1, so the future is like present.
Oh, okay.
So this would be like the I plus 1 in the Neural Turing Machines. To just focus your attention on the next element, the element that was written after the one that we just read.
And I still have a question. So could you please clarify this part? Yeah.
Okay, so we want to somehow discount the values of the previous linkage matrix.
If what?
If we have written to the jth position, so it is now useless to have the edge from I to j. So if we overwritten the element j, then the position at index j is useless for us in the terms of this matrix.
Why?
Because we overwritten this, it is not precedent anymore.
Yes, but
So we have to forget this row. This column.
I still don't understand. So okay, we have written to the cell J, and now if we had this linkage L, we could knew that now we need to move towards I.
No,
And you are suggesting to forget this linkage.
no, I suggest to forget, for example, oh, so this is the linkage matrix. Here's the row I, and here's the column J.
Right.
So if we try to overwrite in our memory bank the ith position and the jth position, then all of those elements in this column and in this row should be changed. So we should forget the previous values of it.
Ah.
And this is why the formula looks like this. Okay.
I see.
So this is one cool thing in differentiable neural computers, and the second one is allocation. So do you have any more questions about this? Because I'm going to raise it.
Is it large, the matrix? Like, what is the typical amount of memory?
N by n, so it's a number of memory elements.
Yeah, but what is like the typical amount of memory in a
100. 100 by 100 is the normal matrix to store. Okay. So
So now we're able to learn the associative dependencies between different types of events, right?
yes, exactly.
And our memory is very flexible. We may learn something, we may forget something if needed. Yes.
Okay. And now we want to avoid interference in the writing. So, for example, we will generate the memory usage vector u, which elements will be from 0 to 1. If it is 1, it means that we are not able to write to this position. And if it is 0, it means that the current position is completely empty. So this is some notion of allocation and freeing mechanism. So all right, let's again write the formulas for it. So, all right, we have the controller. The controller outputs the so-called free gate. they mean how much we would like to erase information from the elements. So from free gates, we compute something a bit opposite for it, which is retention weight. Retention vector. So it is given by this formula, it's product over all read heads. So they consider that we have multiple read heads. Times 1 minus VTI, this is the forget gate, F. And the I here means that the forget gates for the read head over I. Times the current read vector. So T, the previous read vector. So what it is, if it is 1, then in the ideal case, if this is 1, then all those are 1s, so those are 0. So we retain if we did not forget or we did not write. So this is like not A and B. Alright, so from the retention vector we generate the usage vector that we've talked before. So usage vector. So, and here is the most interesting part. So U at the timestamp T equals to UT minus 1 plus WT minus, actually the most interesting part would be the next one, sorry. WT minus 1W times, this is the element-wise product, UT minus 1. And finally, multiply the whole thing by the retention vector. So this thing is logical OR in the real notation. So A or B actually equals to A plus B minus A times B. Because if those are 1s, this one is equals to 2, you subtract 1 and get the 1. Okay, so this means that that the memory position is used if either it was used in the previous position or it was or you just wrote this. And then you multiply it by retention so that if you freed the current position, then you'll be able to write again. So this means like it is used if it was used in the previous timestamp and it was not freed currently.
So retention, what is the Russian variant?
Сохранение. So it is the opposite of forgetting. Okay? Right, now the funniest part. Yes? Yeah. So now we need to write the allocation vectors, which would say into which positions we should write. And this equals to this one. So allocation vector at the position I is 1 minus U at the timestamp T at I. And I is the ith value in the sorted version of vector U. Times the product of K equals from 1 to up to this point, I minus 1 of the UT I. Alright, so the question is this differentiable? You see, you have to sort the values here.
Right.
Compute this. And the answer is yes. And it is really cool. Because if you consider the merge sort, all you have to make differentiable is the sorting of the elements of the vectors of length 2. So if we have the vector AB, then the sorted value vector would be minimum of A and B, and the maximum of A and B. But you can differentiate those things. So let's try to do this. So derivative of maximum of A and B by A. So what it is? If A is less than B, then it is not used in the computation. So it is 0 if A is less than B. However, if it is larger, then then this value will be equal to a, and so the derivative would be just 1. So if a is greater or equal to b.
Not exactly. If a is strictly greater than b, and if a equals to b, then there should be an interval from 0 to 1,
Well, yes,
and this is called subgradient.
Yes, sure. But let's consider 1. Oh, okay, for formulas, let's write
It's a greater.
1. Okay, so now this thing became differentiable. You can sort by merge sort.
For 2 elements, yes. But if the number of elements is, say, 100, then what?
To join two arrays, you have to perform sorting of tuples.
Well, we can differentiate, say, maximum. But can we differentiate, say, 17th position in our sort array?
We don't have to. We only need the values. We don't need to know the exact position. So we need to perform sort, but not the argument sort.
For me, no.
Oh, why?
I still do not understand. So, what arrays are sorted here? U or A?
U, the usage. And we use it to compute the vector A, which is allocation vector A. So, all right, let's consider an example. Okay. So, for example, if U equals to, for example, 0.9, 0, 0.1, then what will be the allocation weights? So we sort those values, and the least one will be 0. So here it would be 1 minus 0. So here would be 1. Okay. So next we go to the second smallest position. It is this one. So we take 0 times 1 minus this value. So this would be 0 times 0.9, which equals to 0. And the same for this. So the allocation vector would have 1 in the only empty position. So the idea here is if we have empty positions, totally empty, then we surely must write to them and not to perform some interference. If, for example, we do not have the completely empty positions, for example, if u equals to 0.9, 0.1, 0.1, also notice here that we don't make them sum up to 1. Those are just independent values from 0 to 1.
Right.
So then the A would be what? So, alright, the least one is 0.1. This one will be 1 minus 0.1, which is 0.9. 0.9. So now we go here. We multiply 1 minus this value, which is 0.9, by this value, so 0.1. And finally we get 0.09. And what for this one?
No, the same procedure.
Yes, okay. We will get 0.001, just like this. Yes. So we multiply 0.1 3 times and get...
right.
No, I think we need another 0, right?
Too much.
No.
No, all right, 2 zeros.
2 zeros.
Right, so here's how the allocation mechanism works. So the final formula is a really strange one.
Wait. And why is it differentiable?
The sorting? Because of the merge sort. In the merge sort, okay, let's consider even not the merge sort, but the simple two loops sort.
Bubble.
Bubble
Well, it's not actually bubble. So what would it be for I from 1 to n minus 1, for j from I plus 1 to n, if... Sorry? Yeah, insertion sort. if AI is greater than AJ, then we swap them. Swap AI.
So you want to say that since the sorting algorithm consists of differentiable
Yes.
elements, then the whole procedure is differentiable, and then we can differentiate.
Yes. And what I wrote here is this part. So it just sorts the tuple.
Okay.
Okay, so the final formula is the right vector, which will take the allocation vectors and write to those positions. However, it has a slight modification. So right vector timestamp t equals to the guarding gate, g e. So, and then the gated average, weighted average of the attention vector plus 1 minus the value of the gate attention times the CTW. So, all right. So what we can see here are the three parts. The first part is that we have the guarding gate. It will not allow us to write if it is 0, independently of all other weightings. This is one thing. Another one is we compute the weighted average between the allocation vector and the content-based retrieval. So this means that you still can ignore the allocation if you use the content retrieval. So why? Because the content retrieval usually focuses on some main parts. It is usually used for overwriting the elements, while the allocation is used to storing new elements. So this one would allow us to overwrite in the one iteration, and this one just to store the new values. All right. So here's the final formula for writing. Okay. So let's now consider a couple of examples. Actually, the paper is really cool because they had really funny illustrations. So, for example, they considered the tasks on the graph, and as an example, they took the subway graph of London subway. They considered two tasks. One is finding the shortest path between the nodes. Another one is traversal task. So you say that you start in this position, then you move to the west using the red line, so you move here. Then you say that you move to the south with the yellow line and so on. And then you're asked in which node are you now, or on which station. Okay, so for the task of finding the shortest path, they inferred that the differentiable neural computer learned to use some sort of the BFS algorithm, the breadth first search. Right. As for the traversal, it first of all stores the graph definition. So here are the edges. Then it has two read heads. The one stores the beginning, and then the other stores the positions into which you moved. And then during the generation, you are given a couple of iterations to think. Then you start attending to the nodes in the order of appearance. So, for example, you're asked to move from one station to another, and you jump using this mechanism to the new station. So you start here, you jump to here. So then you read the query that you want to move using a central line to the east, and you understand that the new value is this one. And so after jumping a few iterations, you output the final answer.
And how can it help us in finding the shortest path?
In the shortest path, it can still jump through the edges. It is given some time to think. So after each iteration, it makes the breadth of the search broader until it reaches the target node. And finally, when we ask it to provide the output, it outputs the shortest path that it found. So actually, those edges are not weighted, so BFS is capable of solving the problem.
Is it human who encodes this BFS?
No.
Not a neural network.
No, it is a neural network who encoded, and by inspecting the read and write weights, they found out that it is some sort of a BFS. So, for example, you would see here something like attending to this one, then in the next position you attend to a lot of them, and then more and more and more until you highlight the required node. So actually they didn't include this image because I think because it would be really strange, because you see here is like one, a node here will be enormous number, here's much more, and so on. It wouldn't be.
So I may simply formulate that I need to go from Bond Street to, say, Euston Station.
Yes.
And the neural network will provide me shortest path.
Yes. The sequence like this, so like take the central line to the east.
Mm-hmm. But how can we guarantee that this is the shortest path, not just an arbitrary path?
Well, the target is the shortest path. The target they've trained it on.
So we train.
Yeah, they trained on the random graphs. So at the beginning of each query, you provided the structure of the graph, which contains of the triplets, which is the beginning of which is the first node, the name of the line, and the second node that it connects. So, all right. For example, here would be the bank. The second would be like the black line, and the last one would be mortgage.
Mm-hmm.
Yes.
Well, the underground is in some kind of planar graph. What kind of graph there was in the training set?
Random graphs. They weren't forced to be planar. Just, I think they had the maximum number of nodes in the graph, and maybe the maximum number of allowed edges, and then they randomly drew them.
The question is the mean degree of node in graph, or
I don't think they had any constraints on that. All right. So another cool example is the family tree inference task. So here how it works. Well, all right. I hope it will work, but it doesn't. Let's try again. All right. So luckily I saved the link. So here how it goes. It has been provided with tuples, which are the, for example, Charlotte, Ellen, and Ellen is the father of Charlotte, and so on. And they provide it with a lot of family dependencies. So like brothers, mother, father, the sisters, and so on. Right. So here's the graph. Now we queried who is Thetis, a maternal great uncle. So they provide it with the notion that maternal great uncle is mother's 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 son. And here it is able to find the needed relation. Okay? So you want to see it again? Right, so see? So now, mothers, yes? You go to the mother, again, mothers. You go to her mothers, and so on.
Great uncle. One may go crazy. I'm trying to imagine who is it? Maternal great
but
uncle.
they provide it with the notion that it is mother's 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 son. Okay, so let's summarize it. We've covered actually 5 papers, but the main data structures that we've covered also are the following. So arrays and associative arrays can be done with the Neural Turing Machines. Stacks, DAX, queues can be done also. They were described in this paper that it was called Learning to Transduce with Unbounded Memory. And the final paper is this one, which also proposes stack and also the double linked lists. Right. So another two papers were mentioned earlier in the slides. So, all right. So now I want to ask you a question that I will not argue about. So it is just a thought, which I think is really cool. So the question is it possible to have a neural Turing machine, a universal neural Turing machine? So what is a universal Turing machine? It is the machine that is capable of running, of simulating any other machine. So it, as an
Any
input,
other Turing machine.
any other Turing machine. So as an input, it gets the some compressed view of the Turing machine and the output. And as the output, it provides the run of that given Turing machine on this input. Okay?
Mm-hmm.
And so the question is it possible to have universal neural Turing machine?
Why not?
Well, I mean, practically no, because it would require unbounded amount of memory.
Okay.
But theoretically, maybe.
Alright, so here it is really cool because what is universal neural Turing machine? You would give it the weights of some other network, and it will have to simulate the network by its weights. I think it's really cool.
I mean, if we already know that recurrent neural networks are
Yes.
Turing complete, so from theoretical standpoint, it doesn't make any difference
Yes.
if we introduce extra features like these read-writes, heads, and memory. So, I mean, from theory perspective, it's already enough to have evidence even without LSTM features. But from practical standpoint, we would need some infinite amount of resources to guarantee this universality.
Yeah, sure.
I would be a bit more optimistic. From my point of view, it doesn't seem to be extremely difficult problem since we're already given formal description of the algorithm of neural Turing machine.
Yes.
And if we are given neural network that plays the role of universal neural Turing machine can potentially learn how to simulate all primitive blocks in this formal description.
Yes.
And then it doesn't seem to be something extraordinarily difficult.
Yes. Okay. So we have some two different points.
Well, I actually tend to
So now I
agree
may
with
start fighting.
No, I
No,
actually would
I
say
said
that your point makes a lot of sense, and now I'm a bit inclined towards your idea and argument. I mean, yeah, really, just think of interpreters. Interpreters are in some way those universal machines. So, yeah, maybe you can actually build a neural interpreter.
So there may be a lot of points of views. I don't think that somebody experimented with this. I think this would be quite cool. So anyway, thank
In
you
a
for your
couple of
attention.
years, we'll see the results. If DeepMind succeeds, we'll know. Okay, any more questions to our speaker? If not, then let us thank him for very interesting talk.